What's up guys, probably the last video on rates today. This time we're looking at Maxwell Boltzmann Distributions, which is pretty much the main thing you need to know at AS level. Before we get into it though, please like, subscribe and share. Try and grow the channel and get to as many people that will find it useful as possible. Let's get into it. So remember, in order for a reaction to happen, we need three things. We need a collision, we need activation energy, we need correct orientation. If any of those things don't happen, no reaction takes place. If all three of those things happen, then a reaction does take place. That's our idea around collision theory. And Maxwell Boltzmann distributions basically show us what proportion of the particles reacts. So this is what a general one looks like. First thing we need to know is the area under the graph represents the total number of molecules. Area under curve equals molecules. Obviously you can all read graphs, you're doing A-level chemistry. Here we're looking at the number of molecules. Sometimes this can be fraction of molecules and that'll make a subtle difference. We'll worry about that a little bit later on. And across the bottom we've got energy. Now first thing we need to know is we do start at the origin, right? We start at 0, 0. And that's because no particles can ever have zero energy, right? Which means that all molecules will have at least some energy. That's what we need to know for starters. Now, the peak of our graph represents the most probable energy. Peak equals most probable. And last thing, we've got this bit which represents the activation energy. And so at that point, anything under this curve will react. What we also need to know is this will never touch the bottom, right? So here the idea is that there's no upper limit to the amount of energy that a particle can have at any given time. We're really talking about average energies most of the time. So never reaches the bottom. Cool. So now we need to know what effect different factors have on this, right? So our first one, we add a catalyst. Now very, very simply, all that's going to happen here is now our activation energy is lowered. Let's make that a bit smaller. So this is our new activation energy. Here with catalyst. And hopefully you can see why now we're going to get more reaction, right? So more particles have at least the activation energy, right? Because that activation energy is now lowered. So when we add a catalyst, that's the only thing we need to add. We need to show that the activation energy is lower. Next bit. So here, temperature. Now we can think about this in a couple of ways. We can think about the temperature increasing. We can think about the temperature decreasing. Now, if the temperature is decreasing, there's a couple of things we need to look to do, right? The peak will shift to the left. And we need to make sure, not only will it shift to the left, it will be higher. We also need to make sure that the energy then falls below, or the fraction of molecules then falls below the original line, right? So that's the couple of things we need to make sure we include. So we need to make sure that we need to make sure that our EMP, sorry, is shifted to the left, and we need to make sure that everything else is lower. Because remember, the number of molecules hasn't changed. So if this was the number of molecules or the fraction of molecules, this will look the same. We need to make sure that this EMP is higher than the EMP of the higher temperature. We also need to make sure it's shifted to the left. So you can see here that more of our particles are over on this left-hand side. We should be able to see as well that now less of our particles, less of our molecules have at least the activation energy. Yeah, so again, let's fully label this. We've got a lower EMP. Nice. And now we'll do the higher temperature in red. So red, that will just work the opposite, right? So again, we're comparing it to our purple line. This time, our most probable energy should be to the right of our most probable energy here. And it should also this time be lower. And then the rest of our line is going to go above our purple line, right? So we can make a little marker for where we're aiming for our peak. And then everything else will stay beyond. We again need to start at the origin. So we come like so. Get something that looks like that. And again, this time you should probably see that our we've got more particles with at least EA. And again, our EMP, our most probable energy is here. Right, we need to make sure we label the peak. Nice. Higher EMP. Perfect. Next, we need to look at concentration. So this is where we will get a difference between fraction of molecules and number of molecules, right? So let's make two different graphs here. And let's start with concentration. Let's start with fraction of molecules. So here, if we doubled the concentration, in terms of fraction of molecules, nothing would change, right? It would still be the same number or the same fraction of molecules that had this EMP. Essentially, we draw exactly the same graph, okay? For number of molecules, this time it would go the other way, right? So say if we halved the concentration, at this point, everything would be halved. It'd be something like this. So we'd have the same EMP, and then again, it would be something like this. So what we're aiming for here is to have essentially half the area underneath the graph, which is easier said than done, but it may well look something like this. Remember, we need to make sure that this never touches the bottom, as is the case with all of these. Again, we're probably going to have about part molecules with the A. So they're big different, and again with half the concentration here, because we've got fraction of molecules on the left, that's going to look exactly the same. So important to note, it will make no difference for any of these three, whether we're talking about fraction of molecules or number of molecules. The only thing that will make a difference is when we're talking about concentration here. Pressure is going to have a similar impact. Basically, the sort of task here is to try and memorise this information, right? Give that a go. There's a lot to be going on with. Let's look at what we did last time. So, here, we've got three more that we should have given a go. So again, let's compare to that first one. We've got large, now our surface area is lower. Actually, let's compare 5 and 2. So we've got large, our concentration is the same, our volume is the same. So we need to make sure, let's go for green here. So comparing to blue, this is going to be slower, but it's going to have the same peak as blue. Yeah, perfect. Next, 5. We're small again. We're small. Let's compare to 1. We're small. Concentration of 2. Volume of 50. Our temperature's increased. So if we think about CNV, there our concentrations stay the same, but our volume has doubled, which means our rate's going to be the same, but our number of moles is going to have doubled compared to 1. We've also got an increase of temperature here. So what we're going to see is this same trend here, more or less. Let's use orange for this. Again, I'm going to say this is much more than double the rate because we've got a much higher temperature. But in reality, it'd be tough to know where it is in comparison to this one. And last one, powder. Exactly the same as number 6, except we're powdered as well. So this is going to be quicker still. Let's use red again for this. So again, even quicker this time, but with that same volume. Obviously, we'd never have anything coming out the other side of this. It should be going straight up, but hopefully you get the general idea. Look, hope that makes sense. Have a go at the stuff from this video. See you next time, and happy revising until then.